Welcome to our review on infinite series. Today we'll cover what series are, convergence, divergence, and some important tests to determine if a series converges or diverges. We'll also work through several examples to solidify our understanding. Let's begin with the definition. An infinite series is the sum of infinitely many terms that follow a specific pattern. We represent this sum using sigma notation, where we start with some index, usually n equals 1, and sum up the terms of sub n as n goes to infinity. When working with infinite series, we're interested in whether the sum approaches a finite value or not. A series converges if the sequence of partial sums approaches a finite limit. A series diverges if the sequence of partial sums doesn't approach a finite limit. It either grows without bound or oscillates without settling to a specific value. Let's look at our first example, the geometric series. A geometric series has the form sum of r raised to the power n minus 1 from n equals 1 to infinity. This series converges when the absolute value of r is less than 1. When it converges, the sum equals 1 divided by 1 minus r. For instance, if r equals 1/2, we get the series 1 plus 1/2 plus 1/4 plus 1/8, and so on. This converges to 2. Let's visualize the convergence of the geometric series with our equals 1/2. Imagine we start with the whole square of area 1. The first term of our series is 1. For the second term, we add half of the original square, so we've now covered 1 plus 1/2, or 1½ squares. For the third term, we add 1/4 of the original square, bringing our total to 1 plus 1/2 plus 1/4, or 1¾ squares. As we continue adding smaller and smaller portions, we approach but never exceed 2 square units. This illustrates why the series converges to 2. Now, let's examine the harmonic series, which is the sum of 1 over n from n equals 1 to infinity. Despite the fact that the individual terms approach 0, this series actually diverges. We can prove this by grouping terms. After the first term, each group contains twice as many terms as the previous group, but each term in the group is at least half the size of the previous group's smallest term. This means each group sums to at least 1/2, and since we have infinitely many groups, the total sum must be infinite. A generalization of the harmonic series is the p-series, which has the form sum of 1 over n raised to the power p, where p is a positive constant. For the p-series, we have a simple rule. If p is greater than 1, the series converges. If p is less than or equal to 1, the series diverges. For example, the series sum of 1 over n squared converges, while the harmonic series, p equals 1, diverges. Now, let's review some important tests for determining whether a series converges or diverges. The first test we'll discuss is the divergence test, also known as the nth term test. If the limit of a sub n as n approaches infinity is not 0, then the series sum of a sub n diverges. It's important to note that if the limit is 0, the test is inconclusive. The series might converge or diverge. Next, we have the comparison test. If we have two series, sum of a sub n and sum of b sub n, where 0 less than or equal to a sub n, less than or equal to b sub n for all n greater than or equal to some value n, then, if sum of b sub n converges, then sum of a sub n also converges. If sum of a sub n diverges, then sum of b sub n also diverges. The limit comparison test is another powerful tool. If we have two series with positive terms, sum of a sub n and sum of b sub n, and the limit of a sub n divided by b sub n as n approaches infinity equals some positive finite value c, then either both series converge or both series diverge. The ratio test is useful for series involving factorials or exponentials. If the limit of the absolute value of a sub n plus 1 divided by a sub n as n approaches infinity equals L, then, if L is less than 1, the series converges absolutely. If L is greater than 1, the series diverges. If L equals 1, the test is inconclusive. Let's work through some examples to practice applying these tests. Example 1. Determine whether the series sum of n squared over 3 to the power n from n equals 1 to infinity converges or diverges. We'll use the ratio test since we have an exponential term. First, we define a sub n as n squared over 3 to the power n. Next, we find a sub n plus 1, which is n plus 1 squared over 3 to the power n plus 1. Now we take the ratio and simplify. As n approaches infinity, This ratio approaches 1/3, which is less than 1. Therefore, by the ratio test, the series converges. Example 2. Determine whether the series sum of n divided by n squared plus 1 from n equals 1 to infinity converges or diverges. For this example, we'll use the comparison test. First, let's analyze the behavior of the general term. For large values of n divided by n squared plus 1 behaves similarly to n divided by n squared, which simplifies to 1 over n. We know that sum of 1 over n is the harmonic series, which diverges. But to use the comparison test properly, we need to establish an inequality. For all n greater than or equal to 1, n divided by n squared plus 1 is less than n divided by n squared, which equals 1 over n. So we have a sub n less than b sub n, where sum of b sub n, the harmonic series, diverges. But this doesn't allow us to conclude anything using the direct comparison test. Let's try the limit comparison test instead, comparing with the harmonic series. The limit of n divided by n squared plus 1 divided by 1 over n as n approaches infinity equals 1. Since this limit is a positive finite value and the harmonic series diverges by the limit comparison test, our series also diverges. Let's summarize what we've learned about series convergence and divergence. A series converges if its partial sums approach a finite limit and diverges otherwise. Some important examples to remember. The geometric series sum of r to the power n minus 1 converges when the absolute value of r is less than 1. The p-series sum of 1 over n to the power p converges when p is greater than 1 and diverges when p is less than or equal to 1. We have several tests to determine convergence or divergence. The divergence test: if the limit of the terms isn't 0, the series diverges. The comparison tests: direct and limit comparison. The ratio test, especially useful for factorials and exponentials. When analyzing a new series, look at its form and behavior to decide which test is most appropriate. Thank you for watching our review of infinite series.